Hello, I'm Molly Haugen, and I am a researcher here at the University of Cambridge. And today I'm going to be discussing some work we've been looking at for how to decarbonize the long-haul heavy goods sector within the UK. And for this particular project, we are looking at what sort of hydrogen refueling station requirements there would be if all long-haul operations went to hydrogen. The focus of this work was really to understand the long-term economics of replacing internal combustion engines with hydrogen. There have been general assessments for hydrogen requirements throughout the UK that have been published, but they primarily look at sweeping generalizations and don't focus on areas where there are high traffic densities compared to low traffic densities and what that then means for the economics for the UK. Countries such as Germany have done these detailed analysis, which give a much more in-depth view of what the requirements are moving forward down this energy vector. Within the UK, other future fuels such as ERS have been looked into, and they also include phasing in this new fuel or new energy source within the UK. And hopefully Daniel will be able to touch on that later on, either today or this week, on the electric road side of things. For this project, the goals were really to determine the requirements for refueling stations within the UK based on the traffic density for the different regions within the UK, and then how that translates to production and consumer costs, both in high and low density areas, as well as centralized and decentralized scenarios. And I'll get into a bit more of what that means later on. In order to look at these questions, we needed to have a distribution model for the energy demand for from 2020 all the way up to 2050 as we decarbonize this long-haul sector. To do this, we just took some basic assumptions, such as the penetration of fuel cell heavy good vehicles, as well as vehicle assumptions with the ranges, average distance per year, energy consumption for a hydrogen refueling or hydrogen vehicle, as well as the tank size. And so the top graph just shows the vehicle penetration rate that we're assuming from 2020 all the way to 2050. And from that, the corresponding hydrogen demand, which is the figure below, for hydrogen all the way up into 2050. We'll also then be discussing what it means to have hydrogen co-located with the refueling stations, as well as a centralized production, and then it has to be distributed to the different refueling stations. So the top dotted box shows that that diagram where the hydrogen is produced on site and then supplied to the refueling station, compared to on the bottom where the hydrogen is produced off site and then is ultimately distributed to the refueling stations as well. In order to do this distribution model, we needed to come up with a few different ways to divide up the UK to look at these different traffic density areas. We wanted to base our analysis off of traffic counts, and so what we did is we took the different regions of the UK and looked at the SRN, which is the figure on the right-hand side. Just for England, Scotland, and Wales will be included in this overall analysis, but just for simplicity, we're showing England here. We then use the traffic counts, which is on the left-hand side for the SRN, to determine the areas of energy concentration and where there would be more either refueling stations needed or larger refueling stations needed to meet the energy demands within those areas. From these two figures, we're able to get percent utilization of M and A roads for the different regions within England, and therefore determine the refueling station size required in those different areas. This is ultimately the result of looking at how many refueling stations are needed throughout England from 2020 all the way up to 2050. We see an increased number around 2040, and this is because there are more smaller stations. And as the energy demand actually increases, we then see that those smaller stations are no longer needed as the larger stations then come online. So the smaller stations, the green and red lines are 220 2,250 to 4,500 kilograms of hydrogen produced per day. And then the larger stations, the blue and the yellow, 9,000 and 18,000 kilograms of hydrogen per day are shown as well. The black line is then the total number of stations. So as you see the total station increases with the hydrogen demand that we had on the previous slide, and is able to supply the correct amount of hydrogen to fuel the long haul freight within England. So this is the total number of stations, and so this is about 438 stations that will be required in England. The overall cost, however, depends on how hydrogen arrives at the station. So the different scenarios that we looked at were a decentralized electrolysis scenario, as well as two centralized scenarios, both for electrolysis and SMR with CCS. This map below shows where these centralized locations would be in England, based on a variety of optimizations for producing hydrogen within the country. And ultimately, this is what will dictate the transport and distribution costs that will ultimately be associated with the levelized cost of hydrogen, as well as the annualized cost of producing hydrogen, hydrogen economy to England. Also contributing to that is the size of the electrolyzers that would be used. So this is obviously for the two different electrolyzer scenarios that we have, or excuse me, electrolysis scenarios that we have. And as would be intuitive, as we increase the size of the station, so this is the colored dots, as we increase the size, the capital cost per kilowatt decreases. So the different colored numbers correspond to the amount of hydrogen produced per day. And this also corresponds to the total size of the electrolyzer, which is on the bottom axis. Then the capital cost per kilowatt is on the y-axis. And what we were able to show with this is, as we increase the size of an electrolyzer, the capital cost decreases. And so if we're operating really small hydrogen production plants, the overall cost will be then increased, and therefore the consumer cost will also increase. This is also very reliant on the load factor at which these plants are operating. So if they're only operating at a 50% load factor or 50% capacity, the cost would then obviously increase if they're not optimizing their size for the demand at that station itself. So, so although it might be cheaper to have a larger station if it's operating at 100% capacity, if it's not operating at 100% capacity, the overall levelized cost of hydrogen would therefore be inflated as well. What we can then use, we can use these hydrogen production costs to then give a levelized cost of hydrogen that includes the variable, fixed, and replacement costs as well. So this is the overall production cost for hydrogen at an 18,000 kilogram per day facility. Just to give an idea of how they change from 2030 to 2050 based on the different costs that are increasing, as well as the three different scenarios. So here we have centralized electrolysis, decentralized electrolysis, and centralized SMR with CCS. The increase in centralized to decentralized electrolysis is because these decentralized cases are often going to be smaller stations, and therefore they have a higher capital cost, which is the blue portion at the bottom. And the electricity costs are going to be slightly increased as well, just as they're operating less efficiently for these scenarios. As we move to 2050, the cost actually increases as electricity becomes more expensive. This is seen in a few different reports where the cost of electricity is forecasted to increase as we move to renewable energy and becomes a bit more expensive to operate. To no surprise, the centralized SMR with CCS is the least expensive scenario that we look at here. However, as we all know in this group, that the cost is not the only factor that needs to be considered when we look at future fuel vectors. We really need to look at that CO2 component as well, and hopefully that'll be some future work in this. So we see the centralized SMR is much lower, but if we're actually able to reduce carbon is the question. If we then take that production cost and include both transporting it and dispensing it based off of the different scenarios that we have, we're then able to get a total annualized cost in billions of pounds per year from 2020 to 2050. And what we see is that the decentralized and centralized electrolysis scenarios are very similar per year compared to the centralized SMR with CCS operating cost per year. And this is again due to the variables that we discussed on the previous slide, where the production is really dominating these annualized costs. Along with the annualized cost of hydrogen, we can look at the consumer cost of hydrogen. What this graph shows is the consumer cost on the y-axis and the differences between 2030 and 2050. But importantly, it shows the differences in the capacity sizes for the electrolyzers that we've used in this analysis. 600 kilograms of hydrogen per day shown in the purple and on the left-hand side, and the orange color, 18,000 kilograms per day shown on the right-hand side of the two different years. What's important to note here is the difference of extremes. So for a vehicle that is operating around 127,000 kilometers per year, this equates to about 17 grand a year in 2030. This difference between refueling at either at a small hydrogen refueling station that has co-located production, or a refueling station that's getting their hydrogen from a small production plant, compared to a station that is able to either get hydrogen from a really big operation or has it co-located at the refueling station itself. These differences highlight the importance to understand what the subsidy requirements are going to need to be for any future fuel using hydrogen. For really low density areas or low traffic density areas that only require small electrolyzers, the cost of hydrogen in those areas is going to be significantly more than in high density areas that are able to have much larger electrolyzers. Again, this difference will then need to be addressed to maintain these smaller fleets in more remote areas. So our work focused on the capital cost, the annualized cost, and the consumer cost required for a hydrogen refueling station network within England and within the UK. Here we have a quick comparison to other work that has been published by Ricardo, by the SRF, and by a group out of Germany. So Ricardo's in the black, the SRF work is in the light blue, and the green is the work out of Germany. And for our different scenarios, the one we have the most comparisons for is the hydrogen decentralized electrolysis, where Ricardo has is significantly lower than our estimates, and then the estimates done in Germany are also slightly higher than ours, but within our sensitivity that we have for this. So quickly, some conclusions. We were able to provide a methodology for allocating refueling stations across England, as I shown here, but we will add Scotland and Wales. We were able to give an annualized and levelized cost of hydrogen for 3 different scenarios: centralized SMR, and then central and decentralized electrolysis, including production, transport, and distribution. And we're able to compare that to other studies that give a more broad analysis for the hydrogen network. There's a load of future work that can be done. Importantly, the CO2 work needs to be done, as well as the grid requirements for the 2 electrolysis scenarios, as well as what there needs to be as far as energy storage at each of these stations to maintain system resilience. So what sort of storage requirements are going to be needed to ensure there is no fuel shortages for a hydrogen network. So with that, I will thank you, and I would like to thank the SRF for allowing me to talk about my work today.